11 cents. Coins of 1, 2 and 5. What is the fewest coins that make 11? 5, 5, 1. 3 coins. Sounds easy. Until the numbers get large. Let's build the algorithm that always finds the minimum. This is the unbounded world. Every coin has unlimited supply. You may reuse the same denomination as many times as you like. And that single freedom is unlocked by one tiny change to the recurrence. Here's the problem. Given coin denominations with unlimited supply and a target amount, return the minimum number of coins that sum to the amount, or -1 if it's impossible. Let's define the state. F of I, t is the minimum number of coins using coin types 0 through I to make amount t. At every state we face one choice. Do we take coin I or skip it? If we skip coin I, the answer falls back to the previous coin type, f of I minus 1 t. Same target, one fewer denomination to work with. If we take coin I, and we only can when its value is at most t, we spend one coin and reduce the target by its value. But what's the index? We recurse into f of I, not f of I minus 1. We stay on the same coin because we are allowed to use it again. Put them together. F of I, t is the minimum of skipping the coin or taking it and staying. The base case, with only the first coin, the answer is t divided by that coin if it divides evenly, otherwise infinity. And this is the entire secret. In the 0-1 knapsack, take recursed into I minus 1. Use each item once. Here, take recurses into I, reuse forever. One index. That's the whole difference. Now let's turn the recurrence into a table. Rows are coin types, columns are the target amount from 0 up to 11. We fill it bottom up. First, the base row, using only the coin of value 1. To make amount t with ones, you need exactly t coins. 0, 1, 2, 3, all the way across. Now each data cell takes the better of two options. Not take, look straight up to the row above. Take, and here's the reuse. Look left, along the same row, to the cell at t minus the coin's value, then add 1. See the difference visually. The not take arrow points up to the previous row, but the take arrow points left within the same row. That sideways arrow is unbounded reuse, made visible. When the table is full, the bottom right corner holds the answer. For 11 with coins 1, 2 and 5, 3 coins, and if that cell still holds infinity, no combination works, so we return -1. We can shrink the memory. Not take reads the row above, so keep a prev row. Take reads the current row to its left, so keep a cur row. Two one-dimensional arrays, and the answer is identical. The cost? We fill n times amount cells, each in constant time. Time is ordered n times amount. Space, with the rolling trick, is just order amount. 3 traps to avoid. 1. Writing take as f of I minus 1 out of habit, that's the 0-1 answer, and it underuses your coins. 2. Forgetting to translate the infinity sentinel back into -1. 3. Keep infinity around 1 billion, so 1 plus infinity never overflows. So here's the takeaway. 0-1 versus unbounded is exactly one index. Take into I minus 1 means use once. Take into I means reuse. Everything else about the index target machinery is identical. Next time, same reusable coins, but instead of minimizing coins, we count the number of ways to make the amount. That's coin change 2. See you there.